Good afternoon, ladies and gentlemen. My name is Katerina Piechko, and today I have the honor of being the Master of Ceremonies at the third GRIPS SDG Award Ceremony, a truly noteworthy event. In this time of political, economic, and social change, the United Nations Sustainable Development Goals have become more important than ever. We at GRIPS have been contributing significantly to the achievement of the SDGs in a number of ways, including the annual presentation of the GRIPS SDG Award. The winner of this year's award is GRIPS graduate, Mr. Mohammad Faiz Syed from India. He is joining us online today, and later he will speak to us about his award-winning project. At this time, I would like to invite GRIPS Acting President, Professor Masako Kurasawa, to give a congratulatory address. Professor Kurasawa, please.
Good afternoon, ladies and gentlemen. Welcome to the third GRIPS SDGs Award ceremony. It is my honor and privilege to confer the third GRIPS SDGs Award to Mr. Mohammad Faiz Syed for having played a leading role in developing and operating a rainfall-based hydrological modeling technique for automatic flood forecasting in India. I would like to congratulate him on his achievements in the project entitled 3 Days Advisory Flood Forecast System of Central Water Commission in the Government of India. In 2015, the United Nations adopted the framework for the SDGs to achieve a better and more sustainable future for all. Here at GRIPS, from the time of GSPS of Saitama University, we have long focused on achieving what the SDGs now point to. Our alumni, in other words, have been equipped with the capacity to tackle many targets of the SDGs in their respective work. So we have launched the GRIPS SDGs Award Contest in order to promote innovative efforts by our alumni towards realizing many targets of the SDGs. We wanted to honor and also learn from the good work of our alumni. The first award was conferred to Mr. Mohammad Sajjad Mughal for his work to design and implement a project to enhance the dairy sector in Pakistan. The second award was conferred to Mr. Anwar Sanusi for his leadership and management role in designing and implementing the major projects of the Indonesian government for village development and poverty eradication. Both award ceremonies have been a great occasion for us to learn from the awardees' insights and activities. This year, we have received many applications from our alumni from Asia, Africa, Europe, and Latin America. And after careful and rigorous examinations and discussions, we have decided that this year's award should go to Mr. Syed. The selection committee highly evaluated Mr. Syed's contribution as one of the key players in developing and implementing the novel, fully automated, easily accessible flood forecast system, which is capable of providing the flood warning 3 days in advance, when it used to be given only 1 day in advance. This kind of early warning system is of increasing importance under the warming climate. The system he has helped to create as a deputy director of the project operates nationwide. It has been proven to be robust, durable, and sustainable, and has been successfully saving many lives and preventing economic disruptions since its implementation in 2017. For all these reasons, we are really privileged to confer the third GRIPS SDGs Award to Mr. Syed. We are also very pleased to hear that the skills that he acquired from his training at iCharm the International Center for Water Hazard and Risk Management of the Public Works Research Institute during his master's studies in disaster management program here at GRIPS were of great value in his work to develop this project. We feel so privileged and grateful that we have been able to continue offering this wonderful program jointly with ICHAM. Dr. Koike, the director of ICHAM, is here today, and he will be delivering the congratulatory address later on. Dr. Koike must be as proud as I am of Mr. Syed's great accomplishment. Last but not least, I would also like to express a great appreciation to the director and all the staff members of the Central Water Commissions of the Government of India for their joint efforts to achieve SDGs by reducing disaster risk. Mr. Syed, congratulations, and we are really honored to have this opportunity to learn from your innovative work. Thank you in advance for your presentation.
Thank you, Professor Kurosawa. And here are the certificate and trophy that we will be sending to Mr. Syed. And again, congratulations from all of us at GRIPS. We will now have the privilege of being addressed by our guest of honor. I am pleased to introduce as our guest of honor, Dr. Toshio Koike. Dr. Koike is Executive Director of the International Center for Water Hazard and Risk Management, a research institute under the auspices of UNESCO and a part of the Public Works Research Institute. He is also Professor Emeritus of the University of Tokyo and member of the Science Council of Japan. Dr. Koike's specialty is hydrology and river engineering. He obtained his bachelor's, master's, and doctoral degrees in engineering from the University of Tokyo, where he later worked as a professor. He has numerous scientific publications on water cycle and climate sciences and their application to water resource management and river planning. He has been leading many international water cycle science projects and has been active in intergovernmental science and technology cooperation. Dr. Koike is the recipient of numerous honors and awards, including an award for the contribution to the IPCC Nobel Peace Prize, which he received from the World Meteorological Organization and the United Nations Environment Program in 2008, a science award which he received from the Japan Society of Hydrology and Water Resources in 2015, and a Friendship Award which he received from the Government of China in 2019. Please join me in welcoming Dr. Koike.
Thank you, Professor Pacheco, and Acting President, Professor Kurosawa, distinguished guests and ladies and gentlemen. I'm delighted to be here on this very special day. Congratulations, Faiz-san, on winning the GRIPS SDG Award 2022 for your outstanding achievement of the 3 days advisory flood forecast system of the Central Water Commission, Government of India. I am especially proud because you're an ICHAM alumni member and ICHAM ambassador, and you have completed a great achievement in the field of flood risk reduction, which is ICHAM's main research focus. The 2030 Agenda was adopted at the United Nations Sustainable Development Summit in September 2015. Its preamble states, "We are determined to take the bold and transformative step which are urgently needed to shift the world onto a sustainable and resilient path. To design the path for the world to take, it is essential to understand the interaction between sustainability and resilience. Water-related disasters intensify by climate change can affect various aspects of society. The impact propagate to the goals related to water, food, energy nexus, and the quality of life. Moreover, once society fall into such circumstances, more problems arise in such area as gender, equality, and peace to a great degree. Throughout the COVID-19 pandemic, the world has learned that the complex cascading and systemic risks that are usually implicit in social, economic, and environmental systems can suddenly emerge and threaten humanity beyond boundaries in space and time. How should humanity survive such risks and live with them in a sustainable way? This is a fundamental question. We had a fourth Asia Pacific Water Summit in Kumamoto, Japan, in April this year. At the summit, 17 heads of state and government requested to explore what role science and technology should play when leaders have to make cross-sectoral decisions. Responding to their request, the chair summary of the summit answered 3. Promote water cycle convenience, foster the facilitators, and take an end-to-end approach. Faiz, ICHAM is very happy to continue working with you, the CWC, and your government to achieve these 3 key targets. Again, promote water cycle convenience, foster facilitators, and take an end-to-end approach. Congratulations again on winning the GRIPS SDG Award 2022. Thank you.
Thank you very much, Dr. Koike, for this inspiring speech. And now Mr. Syed, the winner of this year's GRIPS SDG Award, will give a talk about his award-winning project. Mr. Mohammad Faiz Syed is a graduate in mechanical engineering. He joined the Central Water Commission, the highest level technical organization of the government of India, in 2007, after passing a highly competitive examination, the Indian Engineering Services. Mr. Syed has keen interest in the water sector and has been serving in various important positions in India's river and flood management. He earned a master's degree in disaster management from GRIPS in 2015 and was awarded the Best Research Award for his studies. He currently holds the position of Superintending Engineer in the Northeast region of India and conducts surveys, monitoring, and appraisal of various irrigation projects in 5 Indian states. Being a representative of the central government, he plays a key role in the development of the water sector in these states. For his work and accomplishments in irrigation, Mr. Syed has been designated for this year's award. The title of Mr. Syed's talk is a 3-day advisory flood forecast system of the Central Water Commission, Government of India. Mr. Syed, please.
Thank you, ma'am, for introducing me, and good afternoon to all of you. Respected President GRIPS, Masaka Kurosawa-san, Vice President Michi Shita-san, Professor Kijima, Professor Koike, Professor Ohuno, Professor Sugawara, and Professor Pechko. Ladies and gentlemen, I heartily welcome you all to this auspicious event today. As you all know that I hail from India and currently serving the Indian government as Superintending Engineer in Department of Central Water Commission. CWC is an apex, or you can say the highest technical organization in the country in the field of water resources. I extend my heartiest thanks and gratitude to GRIPS and its award committee for conferring the prestigious SDG award to me this year. It's a matter of pride and honor, not only for me, but also for my department. I would take this opportunity to thank my government and my department, CWC, for sending me to Japan in 2014-15 for doing Masters in Disaster Management. Regarding my project, that is 3-day advisory flood forecast system, for which I'm receiving the award today, I must say that it was a complete team effort. It was my director, Mr. Ritesh Khattar, and myself who initially conceptualized it, and later on many young officers from CWC contributed. To name some of them, like Vasant, Pranav, and Nicole, they all are young officers who really contributed to this project. Further, the project would not have been possible without the full-hearted support and encouragement from our chairman, our member RM, and the chief engineer. This award belongs to all of them. Personally, I would dedicate this award to my late father, Mr. Syed Rahmatullah, who has always been my inspiration and a driving force in life. It was he who motivated me to do masters from Japan. Also, I would thank my mother, my wife, and my brother for always loving and supporting me. Apart from an individual milestone, this award is important for our department as it gives our flood forecasting activity a new identity, not only in India, but also abroad. We see it as another feather in CWC's cap. During 2014-15, my training at ICHAM was a great learning experience. During the training course, I not only acquired the relevant skill set and knowledge, but also widened my scope of understanding disasters and flood disasters in particular. I feel happy to mention that I was also awarded the Best Researcher Award during the course of training. Once again, I thank ICHAM for that, especially to Professor Koike-san and Professor Saima, who was my guide then. So ladies and gentlemen, today I'll be presenting before you my project, that is 3-day advisory flood forecast system. Kindly allow me to share the screen to start my presentation. Professor Pechko, could you please confirm whether the screen is shared or not? I think the screen is shared.
Yes, we can see that.
Okay, thank you. So the project for which I'm receiving this award is the 3-day advisory flood forecast system of Central Water Commission. This is the figure, which is the UI, user interface of the portal that we have developed, where actually the all the results gets published. So before getting deeper into the project, let me give you a brief introduction about India as a country, particularly with respect to its water resources. You see, India is a country having an area of around 3.28 million square kilometers. We cater to around 2.45% of the world's area, and we are 7th largest country in the world. Population wise, if you can see, our population is around 1390 million, which is around 18% of the world, and we stand at number 2nd. There are 28 states in India, and our coastline is one of the largest in the world. You can say 7,500 kilometers of coastline. We cater to 4% of the world water resources, and our average rainfall, annual rainfall, is around 1170 mm. There are around more than 10,000 rivers in India, which have length more than 1.6 kilometers. The total annual basin flow is estimated to be 1869 kilometer cube. there are 12 river basins in India which are having catchment more than 20,000 square kilometers. So looking at a glance, we see that we are highly rich in water resources. Now let us see the 10 major river basins that we have in India. The first and the foremost is the Ganga Basin. The catchment area is around 1 million square kilometer, but the Indian portion is around 861,000 square kilometers. So the pink portion that you are seeing is the Ganga Basin. It is one of the most fertile lands that we have in the country. Then the second international basin that we have is the Indus. It is 1.16 million square kilometers of catchment, but only 322,000 square kilometers lies in India. It is also one of the most fertile and prolific basins of the country. The third is the Brahmaputra Basin. It has a catchment area of 580,000 square kilometers, out of which 194,000 square kilometers lies in India. This is particularly the basin where I'm currently posted here in the Northeast region. Then we have the Godavari Basin having the catchment of 313,000 square kilometers. This basin entirely lies within India. Then we have Krishna Basin. This again is a total indigenous Indian basin having a catchment area of around 259,000 square kilometers. Then we have Kaveri, moving downward, we have Kaveri, 81,000 square kilometers. Then Mahanadi is again a basin with a catchment area of 141,000 square kilometers. You see, all these basins are draining into Bay of Bengal. Only it is the Narmada and the Tapi Basin which drains into Arabian Sea, having the catchment of 98 and 65,000 square kilometers respectively. Last but not the least is the Barak Basin, where I'm posted right now, where I'm sitting right now. It has a relatively a smaller basin. It has having a catchment area of around 34,000 square kilometers. So you see, we have a total drainage area of around 253 million square kilometers, covering 81% of the total geographical area of the country. So this is, seeing this map, you can see the entire Indian space is covered with drainage basins. We are relatively rich in drainage basin. So 81% of our geographical area lies in some of the other drainage basins of the country. Looking at the flood problem in India, India faces flood almost every year. So this is a recurrent problem that we face, and we have been facing this from long back. The map that you are seeing on the right side, having a blue portion that shows the flood-prone area of the country. See, most of the northern and the eastern parts of India are flood-prone, and there are some pockets of flood-prone areas in the west and the south also. So to assess the flood proneness of the country, a commission was set up way back in 1980. It was called Rashtriya Baadh Ayog, and it gave its report saying that around 40 million hectares, which accounts to around 12.2% of the total geographical area, 40 million hectares of the country, of the land in India is flood prone. And the annual affected area is 7.17 million hectares, out of which 3.94 is the area where crops are affected. So out of these 40 million hectares, so far, we have been able to provide reasonable degree of protection to around 21 million hectares. And our target, the target of Government of India by 2035 is to take that figure from 21 to 35 million hectares. That is additional 14 million hectares more. If you see state-wise, out of the 28 states, these 11 states are majorly flood prone. And if you can see on the left side, the table that I have given, Ganga Basin itself brings floods to around 5 states. And then the corresponding, like Brahmaputra, brings floods to Assam, Mahanadi to Odisha, Godavari, Krishna, Pennar to Andhra Pradesh, Narmada, Tapi, Sabarmati to Gujarat, and so on. On the right side, you can see the different states that are flood prone. The flood damage, what is the scale of flood damage, annual flood damage that we have? You see in monetary terms, around $734 million of monetary damage is done every year. Loss of life is around more than 650 people. Household damages are more than 1.2 million, and cattle loss is more than 600,000 millions. 600,000. So huge annual flood damage is caused every year in India by floods. This is the major flood event in recent times from 2012 to 2019. You see more than 15 flood events we have faced in the recent times. The idea is to show that in the recent times, the frequency of flood disasters have increased. So this is again some figure that shows you how much damage the flood causes. Let us see what are the main causes of flood in India. You see, when we talk about the causes, both natural and socio-economic causes are there. Socio-economic means man-made. I'm calling these vulnerabilities because these are the weak points that are pre-existing in our system. There are certain natural causes and there are certain socio-economic causes that are aggravating our flood situation in the country. Let us take them one by one. First is the rainfall variability. As you all know, rainfall is variable both in space and time. But in Indian situation, this gets more aggravated because we get 90% of the rainfall, the annual rainfall within the span of 2 or 3 months. The reason is wide variability in space and time. We have areas in India where there are no rainfall throughout the year, and also areas where we have more than 12,000 mm of rainfall annually. Recently, 2 days back, the place where I'm sitting right now in Meghalaya, just 45 kilometers from here is the wettest place on earth, that is Mountain Ram. And just 2 days back, the all-time record was broken. Mountain Ram had a rainfall of around 1,003 mm within 24 hours. So you see, this is the nature of variability as far as rainfall is concerned. So the planning of floods and the planning becomes very difficult. The second is the large drainage areas. As I've already shown you, most of the major river basins in India are over 100,000 square kilometers. So what large basins done is they bring huge amount of accumulation of silt and water inflows at the lower reaches. That is the main cause of flooding in the lower reaches of these basins. Then inadequate carrying capacity of rivers. This is a very common observation that now, due to heavy silting of river beds, degradation of hilly catchments and flood-prone encroachment, the carrying capacity of our rivers have decreased, and slightest of the increase in inflows causes flooding or the embankment breaches there. So this is also one of the reasons why we are having most of the flooding cases in India. Poor natural drainage in flood-prone areas, insufficient slope of depression areas to drain by gravity. Generally, the slope of Indian rivers are high at the upper reaches, but as we move downward towards the downstream reaches, the slope becomes very, very low. Now, this causes extra sedimentation. This causes difficulty in the drainage. So that also is one of the reasons why we are having flood at the lower reaches of the basin. Then obstruction by road and railway embankments and other infrastructural features. It often happens that some unplanned road embankments or infrastructural features come up. They also hinder in natural drainage of the river. Then these are natural phenomena of landslides and glacial lake outbursts that are also sometimes responsible for floods. And finally, the cloudburst. This is also the occurrence of cloudburst phenomena has also increased in recent times. So this also causes flooding to some of the areas. Now let's come to the socio-economic vulnerabilities that we have. The first and the foremost is the low per capita income. The average per capita income of India is around $1,150 annually. Now, what low per capita income does it puts serious constraints on the coping capacity of the people. Their resilience towards flood damage decreases. So that is the reason why most highly densely populated areas are generally flood prone in India. So per capita income is one of the socioeconomic causes that actually aggravates, worsens the flood situation in the country. Then public resistance to flood control structures. Construction of new dam and barrages face strong resistance from people. This thing has started happening in India for some time back. Like there's a huge outcry among the people against the construction of flood control structures like dams and barrages. There are some misconceptions like fear of dam break, loss of land and livelihood without proper compensation, adverse impact on environment. So these misconceptions are there among the public, and that is the reason why they resist towards structure of building of such structures. So the result is the flood control becomes difficult and people get more exposed to flood hazards. And I think Northeast region is a typical example of this, where the entire Brahmaputra reach is almost unregulated. Here there is a huge outcry against all these structures, and that is the reason why every year Assam Valley, Assam lower plains suffer from huge flood losses. Third and last is tendency of living with floods. People living in flood affected areas tend to accept floods as the part of their lives and start to live with it. Such tendency among public is detrimental to the progress of flood management in the country, as people stop pushing hard for flood mitigation measures from the government. It also encourages floodplain encroachment, and during the flood event, people resist evacuation. So these are some of the natural and socioeconomic causes why flood is such a big problem in the country like India. Now, flood management in India has a two-tier system. One is the central government and second is the state government. In central government, like Central Water Commission, my department, so GFCC, Ganga Flood Control Commission, Brahmaputra Board, and National Disaster Management Authority. These are the some central government agencies which look after flood management in India. And then every state has its own department, like Water Resource Department, State Technical Advisory Committee, Flood Control Boards, Irrigation Department, and Public Work Departments. So at the center, basically policy making and fund allocation are done, and the executing part is done by the state government. This is how the two-tier system of flood management works. The tools that we have for flood management is structural and non-structural. The ultimate goal is the same, that is the flood risk mitigation. Through structural measures, we do it by building embankments, levees, and dams. The idea is to control flood. Whereas for non-structural measures, the tools are like flood forecasting, floodplain zoning, watershed development. The idea is to keep people away from the flood. So of late, there has been a shift from structural to non-structural measures. Because of the long gestation period, high cost of that we incur in structural measures, now the government is more interested in non-structural measures because they are mostly cost effective. Now, we have been doing flood forecasting for the last 62 years. CWC has an extensive network of 325 forecasting stations. More than 7,000 forecasts are issued annually in our country, and it gets disseminated to all the concerned stakeholders. We have generally categorized flood into four categories. One is a normal, second is above normal, then severe, and then extreme. That depends upon the gauge level that is attained by the water level in the river. So the flood forecasting network of CWC is spread across 26 river basins. We have a network of around 1,600 HO sites, hydrological observation sites. These sites are further classified into G, GD, GDS, GDSQ, and GDQ. G stands for gauge. G and D, gauge and discharge both are measured. GDS, gauge, discharge, and silt. And GDSQ, this is a full-fledged site where gauge, discharge, silt, and water quality, all the parameters are measured. So we have a network of around 1,600 HO sites. And then out of this, we have 325 forecasting stations. Now, the conventional forecasting method that is adopted in India is gauge-to-gauge correlation method. It is purely a statistical technique which has a very high accuracy of around 95%. but it has some constraints. The few constraints that are there is it has fixed and short lead time subject to travel time available. This is the major constraint of gauge-to-gauge correlation method, that you cannot increase the warning time in this system. No specific way to include rainfall between base station and forecasting station. So rainfall has nothing to do with the system. It has a reach approach and no basin approach, requires frequent updating of correlation graphs. Structures that are there in the reaches that are not accounted for, and difficult in small basins, especially in hilly and flashy rivers. It fails in hilly and flashy rivers. So the entire formulation is manual and there is a human judgment involved. So these are some of the constraints that are associated with gauge-to-gauge correlation. So the demand in the recent time has been for a longer lead time so that our disaster managers are in a better position to take preventive actions. So increasing the lead time has been a main priority of Central Water Commission. To do so, we have modernized our flood forecasting activity, like in the field of data collection. Earlier, it was done manually. Now we are using sensors, telemetry is installed everywhere. Data communication, it was done earlier by wireless system. Now we are using VSAT, satellite system is there. Data processing and forecast formulation, it was done manually. Still we are doing manually, but it is being complemented by mathematical models now. The forecast dissemination, it was earlier personal messengers, telegram, post and fax. Now email, SMS, web portals and WhatsApp for faster delivery of warnings. So modernization has helped us in switching to more advanced and flood forecasting techniques using mathematical models. So what benefits this mathematical modeling technique is giving to us? It has increased our lead time from say 5 to 6 hours to 72 hours. And now I have been told that the current flood forecasting advisory has been giving advice for around 120 hours. That is for 5 days also. The forecast generation has multiple points at the same time. Both level and inflow forecast can be done. Forecasting can be done using basin approach. Earlier it was a reach approach, now it is a basin approach. Better conceptual understanding of the basin, response from hilly, flashy catchments can be forecasted, easy integration with regulating structures, and dissemination become faster, widespread and easier. So this is a simple methodology that we are using. Like we are using the satellite rainfall, observed rainfall, and rainfall forecast as input. Then we are putting these rainfalls into a model which has two engines. One is hydrologic, another is hydrodynamic. Hydrologic engine converts the rainfall into runoff. That runoff is again fed into hydrodynamic model, which routes it and gives us a time series of forecasts, which can be easily interpreted as warnings. So this is the basic schematic view of how we are doing the forecasting using mathematical models. This is the user interface, the landing page of our forecasting portal. Here you can see it is 5 days advisory forecast. Now it has been upgraded from 3 days to 5 days, which is a good thing. So here on the left side, you see there is a text box where you can see the forecast for 1 to 5 days. And then you can also see the type of forecast that it can show, that it is a level forecast or an inflow forecast. And then you can also have a district layer and block layer for entire country. And then we have some information about the rainfall also. So looking at this picture, the entire pan-India information you are getting. Like these markers you must be seeing. The blue markers means that the flood situation is normal at that place. Each marker is representing each forecasting station. Now the color of the marker will change as the flooding situation changes. So this system was started in 2016. It is in its 7th year in progress. It covers around 342 stations, out of which 199 are level and 143 are inflow. It covers 19 river basins and 22 states. It is in full integration with IMD rainfall because we are taking the forecasted rainfall from IMD, which is in meteorological department in India. The system was fully in-house developed and it covers all the major flood prone areas of the country. The update frequency of the system is around 3 hours more than 2,700 forecasts are getting generated daily during the monsoon season. So now let me show you how the system is working. Clicking on the marker pop-ups the forecast for that station. So as I told you, each marker is representing a forecasting station, and the color of the marker is representing the flood situation. So the markers are blue, yellow, orange, or red color, showing the different levels of flooding. So the blue markers, that means normal flow is there. If it gets yellow, that means the water has crossed the warning level. If it is orange, it has crossed the danger level. And if it is red, that it has crossed the HFL, highest flood level. If you zoom in into some area, like this is the Brahmaputra area, if you click on any of the marker, you will get a pop-up which will show you the actual forecast for 3 or 5 days. 5 days. To elaborate on that, I will show you the sample forecast and try to explain that. See, it has two portions. The upper portion is the rainfall portion, and the lower portion is the water level portion. The left, this red line is there. On the left side, we have the historical rainfall, which has actually occurred. On the right side, we have a forecasted rainfall, which we are getting from IMD. Now, on the lower side, corresponding to the historical rainfall, we are getting the actual water level. And on the right side, we are getting the forecasted water level, which is being forecasted by the model. So here we have also demarcated the important levels, like this is the yellow line is the warning level, this is the danger level, and the red line is the HFL. So you can see date-wise, day 1, day 2, day 3, what the situation is likely to be. So this gives you a clear picture about the warnings. Now this day, the forecast has been increased to 5 days now. So not only 3, but you are getting 2 days extra now of forecast. The data that I have used is the real-time, not real-time, but almost near real-time GPM and GS map merged satellite rainfall estimates as constant inputs to the model. 3-day forecasted rainfall in the form of WRF and GFS from IMD. Ground-based rainfall data, ARGs through ARGs and telemetry for rainfall validation. Historical flow and water level data for model calibration. River cross-section and real-time observed water level data for error correction. The constraints are, as I told you, that these satellite rainfalls that we are getting have their inaccuracies. There are inaccuracies in rainfall forecast rainfall also, and the inadequate rainfall gauges and its distribution. Non-availability of reservoir release data, we are not accounting for that, and non-availability of snow and temperature. So we're not also accounting snow melt contribution to the flood. So that constraint is also there. The future course of action is like integration of ground-based rainfall data from IMD at near real-time in grid form. Integration of snow melt contributions, which we are not doing right now. So we would like to do that in future. Integration of reservoir releases. We are not having this data right now, but as soon as we start getting this data, reservoir releases, we will be incorporating that into the system. So overall, the efficiency of the system will improve. Now, let me show you the live demonstration. Since we are lucky that it's a monsoon season is going on, we are into a flood season. So let me show you the live demonstration of the system. See, this is the live portal we have entered. This is the current situation in India right now. Most of the western or southern portions are dry, but the monsoon has started taking its effect in the northeast region. Now, if you zoom in into any area, you click on the marker and then you get the forecast. So this is how it works. You can note down the link and you can try it on yourself. So this is all, I think, from my side. Thank you.